All right, let's go ahead. I want to start this session, and just talk a little bit about what we're doing today. So this is the Planetary Science session, and in this session, like all the sessions, we have 10-minute slots. And so the speakers are targeting an 8-minute talk, and then there'll be a time for questions and changing over the talk, right? So during questions, we're going to go ahead and switch to the next PowerPoint. So there won't be a chance for extra slides or even to go back to slides necessarily during the questions. It depends on how long you go on your talk. We will have a warning after 5 minutes telling you have 3 minutes left, and then a warning after 7 minutes showing you have 1 minute left. So the speaker needs to pay attention to that. But yeah, that's how it's going to work, and we are absolutely going to stay on time. If you run late, I will cut you off. Okay, so, and this is how we do it in real scientific meetings, right? You cannot run late. And I cut off a colleague at a AGU meeting once. Anyway, so we will do that if we need to, so stay on time. But we're excited to see your presentations and so on. So we have, we also have, where's the pointer? All right, I'll take that. So the pointer, you can advance your own slides with the pointer. And if you haven't used one of these before, I'll show you, but it's very simple. So our first presentation is, excuse me, from Greta Freeman from Northern Arizona University. So come on up. And she's going to tell us about mapping mounds in Utopia Planitia. And yeah, so there it is. That is the laser. And that's forward.
Hi everyone, my name is Greta Freeman. I'm a junior at Northern Arizona University studying geology, and my project is mapping mounds in Utopia Planitia to investigate the origin of Martian volcanic features. Okay, so first of all, what is Utopia Planitia? It is an impact basin located in the northern lowlands of Mars, and it is an accumulation of sediments and lavas and some like volatiles. That's what a basin is. And what is so significant about this region is lots of volatiles and ice have been discovered in this area, and within the accumulation of sediments, we think that there's some pressure that created like eruptions of mounds from the volatiles in the subsurface. And that's what I'm studying, these mounds. And our project goal is to get a statistical idea of the elevation distribution of mound proportions and to characterize the spatial relationship between volcanic features in the surrounding geologic units. And there are these mounds, what I'm studying. We think they're mud volcanoes, which is the sediment that was erupted from the subsurface. And these are just some terrestrial examples of on Earth what they would look like on Mars, potentially. And so the mounds that we looked at a variety of them. These are all smooth mounds, pitted mounds, cratered mounds, and pitted crater mounds. These are to scale. You can see pits, craters. I'm not sure what really formed the pits, but that could just be like a collapse of sediment. And we also looked at shields, and those are like more effusive style mounds compared to the accumulated dome mounds. So we had smooth shields, pitted shields, cratered shields, and pitted cratered shields. These were a lot more difficult to identify just because they just look extremely eroded, and even for the smooth shields, I only found 4, but I'm not even sure if like this is a mound. So, yeah. And then we also had a complex category, and this is just like mounds that overlap each other, and we have just a variety of them. Undivided shield, smooth mound complex, cratered mounds, pitted mound complex, pitted crater mounds, and diverse mound is just like everything altogether. And as for the methods to collect all these mounds on Mars, I used a geographic information spatial software called JMARS that was developed by ASU to map all these features, and I used the CTX global mosaic layer, and these images were derived from the Mars Reconnaissance Orbiter, and 35,000 data points were mapped. This is all just like a small category within the Utopia Planitia. I did not get very far within like the 6 months that I had. But yeah, these are all the mounds that I mapped. And then after I found the locations of the mounds, I attributed the points into ArcGIS Pro and got an idea of their elevation and their geologic units that they formed on. And so for our results, these are just histograms of the elevation and their frequency of the mounds. So elevation is on x-axis, and the frequency of the mound types are on the y-axis. Pitted mound, smooth mound, these are all just the mounds that we have. And you can see that most of the mounds that we found were located around negative 4,000 meters. And one of the reasons why, I think, is because I only looked in a certain like corner of the basin. So like if we looked in the entire area, it'd be more distributed, but this is what we have. And then the complex craters, there's some bimodal distribution around negative 4,000. And that could be due to their age, their geologic unit that they formed on. And the most common geologic units that they did form on were the Hesperian, like early to late, so in that range from 3.6 to 3.2 billion years ago. And during this time, we think that there is abundant volcanic activity and much wetter climate, so that would contribute to accumulation of the volatiles in the subsurface and all the deposition. And then the other unit that we found, where all the mounds were found on, were the Middle Amazonian from 3.2 to 2 billion years. And this was a transition era of colder and arid climate, so that dried out the land, and then, yeah, all the pressure of the sediments and the volcano formed. And this is just a pie chart of the percentage of mounds that I found. I mainly found smooth mounds. That could just be like my trained eye being biased of finding the most like aesthetically pleasing mounds. And so with these let's go to the conclusion. But because we found that the mounds are all located within one elevation, we think that they're sedimentary in origin, so most likely mud volcanoes, because igneous volcanic features would be more sporadic and not like, they wouldn't be elevation dependent. But that's just my theory. We still don't know where the mounds come from, if they're sedimentary or igneous. We did find that mound subcategories vary with elevation and their geologic unit, and distribution among geologic units suggests a relationship between subsurface history and their current mound formations. And I'd like to thank my colleagues for helping me, Grizzle Kubo from the USGS, Holly Rubin, and Paloma Davidson. And I'd like to thank my cat, Ivan, for helping me map on JMARS. Oh yeah, those are my references. But yeah, thank you.
All right, now, a couple of questions? Yes.
You said you get to Carly, you paid $35
I don't know, I just sat at my desk and just like click, and yeah.
Over here, where were the volcano flood that you took pictures? Where were they at?
I think these were in like somewhere in California and somewhere in the Middle East. Yeah.
So you used a high-res imagery before. Did you make your own image suggestions, or did you just use stuff that people had already taken pictures of before?
I just used people's past photos. Yeah.
So mud volcanoes here on Earth, if those are what are on Mars, what does that tell us? Like we understand volcanoes here, it's like regular volcanoes. What does it tell us about Mars?
Yeah. So like on Earth, the mud volcanoes here host like organic materials like they're commonly found in there. And so if we see that on Earth, then maybe there's like life in these volcanoes. But we'd have to go there and find out, but we can't go there. Yeah.
Okay, great. Let's thank her again. All right, next up, from the University of Arizona.
Hi, I'm Travis, and I'm a senior at the University of Arizona, and today I'm going to be talking about my work mapping Martian crustal magnetic anomalies. But Mars is really far away, so I'm going to start here on Earth with our magnetic field. We have a magnetosphere that's generated by a dynamo, and a dynamo requires a rotating convective and electrically conductive fluid interior to form. They're really important because they deflect solar radiation, so that can break down DNA, so not good for life. The Sun, the gas and ice giants, and Earth all host global magnetic fields, but Earth's a little bit different because we are a rocky planet. So another rocky planet is Mars, but in the 90s, the exact nature and strength of this magnetic field were unknown. So we sent Mars Global Surveyor there, among other science objectives. It arrived in 1997 equipped with a magnetometer and electron reflectometer. These were used to characterize the magnetic field, and as you can see in that figure, it measured a patchy and variable magnetic field. So this was interpreted to represent a crustal magnetic field, or one in which the magnetic signatures are primarily generated from surface and subsurface, near-surface features. This is possible due to a mechanism called remnant magnetism. Essentially, you can have iron atoms in an erupting magma, and if they interact with water, they can actually create ferromagnetic iron oxides. So that's a lot of geology jargon, but essentially you can think of these on a molecular level as being little bar magnets, and when they're hot enough in their lava, they are randomly oriented, but then in the presence of an external magnetic field, they will actually align to that magnetic field as they cool down past a certain temperature called their Curie temperature. And then what's special about these ferromagnetic materials is that they stay permanently magnetized after the removal of an external magnetic field. So on Mars, if there was a dynamo, and then eventually that dynamo got removed, any rocks that cooled during that dynamo would in fact show their magnetic signature. So back to the MGS results. This is another famous figure that was used to interpret pole reversals on ancient Mars, but you notice a distinct lack of magnetic signatures over young volcanoes and old impact basins. I think the oldest basin there is Utopia Planitia. If you interpret that to mean that when these impacts formed, there was no dynamo to magnetize the rock, you can get a dynamo cessation date of 4.1 billion years. And just for reference, this is a scheme of Martian geologic eons. So 4.1 billion years would have been about at the beginning of the Noachian. And then in 2014, we sent the MAVEN orbiter to Mars. It arrived in 2014. And this was an atmospheric and volatile evolution probe. So it was actually designed to sample the atmosphere. And because of this, it had to orbit at much lower rates than MGS ever did, about a third of the altitude, I believe. And it was equipped with a magnetometer. So I use the magnetometer data to create a nearly global map of Mars's magnetic field due to crustal magnetism. I say nearly because we left out the poles. This is 60 degrees south to 60 north. And it was modeled using an array of dipoles 10 kilometers deep into the surface. So we set up an array and then iteratively adjusted it to reflect the orbital data. This is known as the equivalent source dipole method. And then one specific weakness of using orbital magnetometers is that it's really hard to distinguish whether these signatures are due to surface features or subsurface features that have since been buried by newer material. So my global map has an altitude of 130 kilometers. So if you were that high above the planet, this is what you would measure. And it has half a degree resolution. And then this specific image is a mosaic of a few different models, or not models, just different regions. After that, we decided to look at some specific volcanic features. The first one was Hadriaca Patera. This is an ancient volcano that has pyroclastic deposits which have since been eroded by water. So we know that water has been there more recently than the volcano erupted. We can also see by the white arrows there that the magnetic field is actually extended in the direction of the pyroclastic flow. And this is a feature that wouldn't be visible at maps of the magnetic field at a lower resolution. So this was taken as evidence for a post-Hellas dynamo because the pyroclastic flow lies on top of Hellas. And this work was presented earlier this year at the Lunar and Planetary Science Conference. The next volcano we decided to look at was Apollinaris Mons. This is near the equator, but when looking at the global map, you can see that the magnetic anomaly is actually kind of offset from the caldera itself. It's a little bit to the northwest, and this is really confusing when looking at topographic evidence, but then following a geological unit map, we can actually see that the magnetic anomaly aligns better with the Noachian edifice over the Hesperian edifice. That's what the NVE and HVE mean. So essentially we can interpret this as evidence that at some point during the Noachian, there was a dynamo that magnetized that material, and then it dissipated or completely disappeared by the time the Hesperian volcano edifice was deposited. And then the final feature I decided to look at was Claridus Fossae. This is just south of the Tharsis Montes. But we again can see that the magnetic field is extended along the geologic and topographic feature. This is again something that would not be possible with lower resolution maps. And we take this to be strong evidence that the surface feature and the magnetic anomalies are correlated. So we're kind of resolving some of the issues of not being able to tell whether these are surface or near surface features that are generating the magnetic anomalies. And then one thing I wanted to leave off on, I just wanted to highlight that in planetary science, we don't always have the best answer right away. We might come up with things, but it's always worth looking into the data more, exploring things and exploring other theories to see if we can learn more about these planets.
Some questions? I've got.
Yeah.
So there's this huge difference between the southern highlands and the northern plains, where you see almost nothing in the northern plains. What do you think is the explanation for that?
Right, so the South Pole is actually a lot older crust. You can tell by the crater size, or the crater distribution, there's a lot more craters. So that crust is actually more likely to be Noachian. That's where the Noachian and Hesperian units are. Another thing though, my advisor did some work in the early 2000s locating like paleopoles, so where the ancient magnetic field was, magnetic poles. And the distribution of that magnetic anomaly curve, it actually follows the paleotropics really well. So that might just have been where water was present and capable of forming these ferromagnetic iron oxides.
Other questions?
On the map, I think it was, of the electromagnetic, like, you know, what you could read from the
surface, basically, there was like a banding effect going on. Do you know what caused that?
Right, so that was pretty strong evidence of pole reversals in Mars's ancient past. We see that here on Earth too in the mid-Atlantic ridge. There's those nice even striations going outward from where the Atlantic Ocean is spreading, I guess. So that's the magnetic field reversing polarity.
You got one more?
So you had a pretty clear evidence of the cessation of the magnetic field. The timing is pretty clear distinction between one period having it and one period not having it.
Mhm.
Do you see anything on the other end, like from like the oldest, like magnetism?
Yeah, it's kind of, so dynamos, like, they require a certain temperature in order to be convective. So when a planet accretes, it'll likely have more heat than it does today. So the dynamo likely existed from formation up until a certain point. So we're more looking for evidence as to where it ended. Yeah, thank you.
All right, next up we have Lucian Morton from Northern Arizona University.
Good morning. My name is Lucienne Morton. I'm a sophomore from NAU. Today I'm going to be talking about the research I conducted this year with Dr. Timothy Titus on the post-midsize asteroid impact long-term flooding hazards. So I'm not talking about Mars, I'm talking about asteroids. Different sizes will have different effects. On the smaller end of things, we'll see something like an airburst where it'll burn up in the atmosphere. There's no actual impact on Earth. But as the size of the asteroid increases, so does the size of the scale of the impact. So we'll see things ranging from airburst to local effects to regional effects, and then finally global effects, meaning mass extinction. Some of the first wave impact effects that we see with asteroids are air blast, thermal radiation, and ash plume, amongst other things. So what is a cascading hazard? That is when a primary disaster event causes a chain of secondary hazards. So for example, an earthquake causing landslides or liquefaction. Over here, you can see a diagram of some of the associated cascading hazards with asteroid impacts and kind of how they're all interconnected. Luckily for us, there haven't been too many large asteroid impacts during humanity's times on Earth. However, that is not so great for research into asteroids. So for that reason, some of the analogous events that we can look at that are a little bit more common on Earth include wildfires, volcanoes, and earthquakes. They have some similar effects to asteroids, and we're able to kind of make an analog between those cascading effects and the ones that we might see with a big asteroid impact. So specifically, since I'm looking at flooding, the most relevant analogous event is wildfires. When a wildfire burns through an area, it makes the soil really hydrophobic, meaning that it's going to reject the water. There's going to be a lot more runoff. It also gets rid of a lot of the vegetation, which really helps keep that soil together. So as a result, after wildfire, we see a really greatly increased rate of flooding. Like, for example, California and Texas, we'll see wildfire season followed by a flooding season. In our timeline here, you can see that we have an impact event causing that same type of hydrophobic damage, and then we're getting multiple months, years of rain events and flooding. It's continuous. So for our project, our objective was to create a simplified model to estimate a total affected population based on two factors: the various hydrophobic radii caused by a mid-sized asteroid impact, and then also the post-impact rainfall events. The question we're seeking to answer is how sensitive is the number of people affected from post-impact flooding based on that thermally radiated hydrophobic radius. And the approach that we're using to answer this question is we'll be using geocloud to calculate flood depth data in various river basins and compare that flood depth data with the population map in order to gain this total affected population. So for our scenario, we're looking at a mid-sized asteroid, which is roughly 800 meters in diameter and releasing about 10.3 gigatons of energy. The 800-meter diameter was previously thought to be just short of the global effects. However, that's a little bit up for debate. The 800-meter impactor is kind of on the edge between regional and global. For a comparison, the Tsar Bomba is the largest above-ground nuclear detonation that humans have done, and that released about 50 to 58 megatons of energy. So this is Big impact. Also, for a preface, this is not real. There is no asteroid heading for Texas. We're good. But our hypothetical impact location is in the Dallas-Fort Worth area of Texas, and the hypothetical date is October 22nd, 2036. So all the rainfall events that we're looking at are after October 22nd, 2036. We also have an assumed evacuation of people within the 2 psi blast radius, which is shown here in that thicker orange radius, because that's the area where pretty much all structures are obliterated. There's not much for these people to come back to. We also specifically tested 5 different possible affected river basins, including the Red River, the Sabine, the Neche, the Trinity, and the Brazos, which are shown over there in our little river basin map. So GeoClaw is a program that solves for the 2D depth average shallow water equations for flow over varying topography. It's typically used for things like tsunamis, storm floods, or storm surges, and other overland flooding. But for our project, we're going to be using it to calculate that flood depth data in the previously mentioned set of river basins based on those various rainfall rates and hydrophobic radii. You can see what our output on GeoClaw looks like in this little animation here. Some caveats of using GeoClaw specifically is that it doesn't actually program for rainfall, so our solution to that was to use a spring in place of rainfall and then just convert between the spring flow rate and the rainfall rate, which is shown in that table there. Also, GeoClaw doesn't account for infiltration, base flow in these river basins, sediment flux, evaporation, or transpiration. We're just kind of hoping that all of these things in a way cancel each other out, so we're able to still get a relatively accurate representation of what this flooding looks like. So the GeoClaw model output was converted to an affected population by taking that flood depth data and basically distributing the total water volume between the lower lying areas of a higher resolution map. Then that was used to then create this fractionally flooded map. So for example, we're getting pixels that are 25% flooded, pixels that are 50% flooded, so on and so forth. That then fractional flooding map was compared with a population map to calculate our people affected. So for a 25% flooded pixel, if there's 1,000 residents, we're estimating that about 250 people are being affected by this flooding. So we tested scenarios ranging from 1 inches at the most mild case to 10 inches per day at the most severe case. And we also tested a hydrophobic radius ranging from 25 kilometers to 175 kilometers at 25 kilometer intervals. So here I have showing our most mild and our most severe case, the 1 inch and the 10 inch per day. I also have 10 inch over there in that lovely little animated GIF. What you might notice with the higher rainfall rates is that there is a bit of a plateau in population just up there. We have hypothesized that there's a kind of saturation of river basins where once you get to a certain amount of flooding, you can't really affect more people. Everyone who's being affected has already been affected. You might also notice this little inflection point there at 75 kilometers. If you notice with the animated GIF, that's when we start crossing over into multiple river basins. And so that's why we're seeing that really big jump in affected population. Also, our most likely case calculated roughly 50,000 people being affected per event, and the worst case was roughly 600,000 people being affected per event. So for a summary, a total affected population was calculated at various hydrophobic radii, which are unknown, in various climate scenarios or rainfall events. The flood damage was found to extend beyond that 2 psi evacuation radius, and the worst case affected population is roughly 12 times higher than the most likely case. Some main takeaways are that the non-evacuees will likely be affected by this long-term flooding, and then also the location and extent of hydrophobic damage, the number of affected river basins, and the population distribution all have a really big influence on this total affected population result. Thank you. Any questions? Yeah.
Oh, so I know that like sometimes wildfires are actually good for like the ground kind of technology.
Yeah.
So is this different from like, you know, the ones that are happening in Texas and California? Is there something different that impacts it, or is it like the same if it's an asteroid?
Well, I mean, we don't have too many asteroids to look at that have had this kind of thermal damage, but we're just kind of hypothesizing that the thermal damage from the asteroid impact is very similar to the wildfires we see. And also, additionally, after an asteroid impact, there are wildfires that are caused that burn further than that radius. So we've hypothesized it's relatively the similar or the same type of thing with a lot of the same type of long-term effects, which may include increasing soil nutrients way down the line. But we're looking really at like the next few months, the next few years after the asteroid impact. How is the hydrophobic soil making it so there's all this extra runoff like how increased is the rate of flooding and how big of a risk of this? Is this something we really need to think about? Yeah.
What was the size of the meteorite that you were using for this?
That was around 800 meter diameter. Yeah. Yeah.
Are you able to use meteorites that hit like before and for data to do this stuff? Like say for instance, the one that killed that.
Like Chicxulub, yeah. We haven't really looked at that one specifically. It's hard to see these kind of like shorter on the geologic timescale type of long-term effects. I don't know if there's a lot of evidence of a lot of flooding happening after Chicxulub, if that's really, I don't know what the right word is, but like if that shows up in the geologic record. If it did, that'd be great, and I would love to use that data, but we haven't really looked into that.
So you were modeling it on the Dallas-Fort Worth area. How many people would be impacted by just like the impact that size rather than just the...
That is actually, my project is a part of a bigger modeling working group that's talking about these long-term effects from asteroid impacts, and there was a group that was working specifically on the initial impacts. I think pretty much you can count anyone within that 2 psi blast radius as having been affected by that initial impact, probably. I mean, hopefully they've already evacuated and they're not actually getting hurt, but all their stuff is going to be destroyed.
Okay, let's thank Lucien again. All right, our next presentation is by Rachel Fry from Northern Arizona University. Come on. Hi. So there's your point. All right.
All right, hey everyone. This is too high. Thank you. Have on time, perfect. Hey everyone, I'm Rachel Fry. I am a senior in astrophysics and astrogeology at Northern Arizona University. I have been working with Dr. Devin Burr and PhD candidate Anna Baker I'm studying dust production on Mars based on specific mineralogies. So there's dust on Mars. I can provide a source, but there's dust on Mars, as we can see in these sometimes globe-spanning dust storms. So dust, there we go. But its origins are not quite understood entirely. So we could have volcaniclastic origins where dust is produced, from maybe volcanic ash just when volcanoes erupt, or when impacts occur on the surface and pulverize the bedrock. Or we have dunes on Mars, and we know that we have active wind on Mars. We can see this from the orbital data. So wind blows sand around on Mars, and so our dust could be from aeolian origin. So when wind blows sand around on a body, any planetary body, sand is a grain size. Sand moves in a process of motion known as saltation, where it bounces across the surface, and as the sand grains bounce, it undergoes collisions. It collides with other grains, it collides with bedrock, and with each collision, the grains can undergo mechanical weathering, where little bits break off, little dust-sized bits, and dust in this instance is a grain size. So these small particles can be released and suspended into the air as dust. There's a couple different mechanisms for this. So if you have a very angular grain, there may be bits that stick out on an angular grain, and as the sand is transported and bounced off, these little bits these little irregularities that poke out, those can break off. You can have chipping from this mechanical weathering process, or we see this on Earth. You can have grains that are coated in like a clay, chemically weathered material. It's a coating. A lot of times it's iron rich. On Earth you see, some very red sands, and if you look at an individual grain, it's quartz. It's not a feldspar, so it's not pink in itself. It's coated in this, kind of reddish, iron rich clay coating. So that's what we're studying. We're actually studying the comparative contribution to dust by the breakoff of these irregularities, disparities from angular grains to the release of this clay coating material as sand undergoes aeolian transport. How do we do this? We do it in the lab, and we use this mill. So we developed an air-driven mill. We use pressurized air to circulate sediment. Air comes in here, we have our sediment in this chamber, and the sediment rolls around the chamber, and it undergoes these grain-to-grain and grain-to-mill body collisions, which simulate the transport, the natural aeolian transport of dunes across the surface of a planetary, sand across the surface of a planetary body. Our mill is about this size. It's, we can run it on a tabletop. We run about 3 grams of sediment in the MAE, the mill for aeolian experiment chamber. And we use high-speed camera to look at the velocities of the grains within the chamber so that we can get up to speeds for transport velocities that we see on Mars so that we can equate the two. We use a couple of these are established analogs for Mars sediments. We have Pisgah Crater tephra, which stands for the basaltic sand. Mars is very basaltic. There's very quartz poor. We see a lot of dunes that are dark. They're basaltic dunes. So that is our, basaltic dune sand. And then we also use coral pink sand dune sediment, which stands in for that is the analog for the coated grains. So we need to do a little processing for the coral pink. We can't just run the coral pink and not have a control. We need a control. So we wash the sediment to remove the clay coating. We boil it in hydrochloric acid for 10 minutes. It removes the coating. We can get, from that process, we can get a comparative or a relative percentage of the coatings for the grains themselves, how much coating is on the grain before we start. But we're also interested in looking at angular grains. Coral pink is very well rounded, so we mechanically crush some of the washed and unwashed grains so that we have angular grains. That way we can compare to the Pisgah Crater tephra between the two different mineralogies of the grains. How does the mineralogy affect dust production for roundness? So that is specifically looking at the roundness value. So we can compare all of them together to look at roundness based on mineralogy and also the release of clay coatings. This is my beautiful hand-drawn chart. So the sediment is run through the mill until either the roundness is, until the mass is no longer decreasing for the sediment. So we're no longer creating dust. And we're also looking at the roundness value. We do an initial characterization of the grains. We use Wiener spectroscopy, particularly for the coral pink dunes, so that we could see if that iron oxide content that is in the coatings is decreasing over time. And we've seen this. So we've run the Pisgah Crater tephra, this volcanic angular tephra, for 15 hours so far. This is our data showing the mass lost from the initial sample, which is showing an increase in dust. The mass is, the sample, the dust-sized particles are being lost through that air exit that I showed on the MAE, but also we sieve it out at each step when we do our analysis. So we're analyzing our grains after each hour in the MAE, and we're showing how much dust is being produced at each time step. Not shown on here is the 3 hours of coral pink that I have done just last week, and that is actually also showing an increase of dust production. It's not quite linear like this though. We showed an initial increase and now it's starting to plateau even after 3 hours, which is expected. They're not angular grains, they're not breaking apart a lot. We're just removing this very, very, very thin coating from the material. So we do expect to see that plateau. And eventually, once, all the angularities in these grains are very well rounded, we will also start to see that plateau effect. So we can start to compare these two different data sets. So we're going to be doing all 4 variations of our coral pink to compare these different values that we're getting for roundness to the Pisgah Crater. But we also have an entire suite of Mars analog sediment that we're going to be running to see how the mineralogies of the different types of sediment that we see on Mars affect dust production. The comparative contribution to dust by the different types of sediment that we see on Mars. Thanks.
I have some questions. Yeah, go ahead.
What effect would a bigger atmosphere density Mars be to the experiment you do?
I'm so glad you asked that question. That's a wonderful question. So studies have been done in the past. I can provide a reference for this that showed that the atmospheric pressure on Mars actually doesn't have a significant effect on this rate of abrasion that you're seeing during transport. The most important thing is getting the collision energies correct. So that is what we use our high-speed camera for, to get an idea of what velocities we're seeing. And then from there we can determine what our impact energies are. If we can equate those to what we see on Mars, then we know that it is something that we can compare to the natural Mars.
Other questions? Yeah, go ahead.
Why did you choose those two sediments?
Yeah, so Pisgah Crater tephra is a young basalt, and it's easy. We have samples of it. It was easy to obtain. It is a young basaltic tephra. It's very angular, so that is a great analog for Mars. There's also a database for Mars sediments, for Mars analog sediments. So we looked at the database to see what we could obtain. The Pisgah Crater was great for what we wanted because we wanted very, very angular tephra to start out with. And coral pink was another established Mars analog sand, and it's also pretty readily available. So if you had some in the lab, we went and just got some. And that was the analog that we needed for those coated sand grains. And Mars is red, so we know that there's iron oxide, on Mars, and particularly on, as coatings on grains.
I've got a question.
Yeah.
How does the dust production depend on the roundness of the particle?
Yeah, so you're not going to see a lot of dust production with a well-rounded particle. So particles will increase in roundness with transport distance. So you think of a piece of sand grain that just got chipped off of a rock, and over time it is transported, it becomes more round. That is something that is established on Earth and in the laboratory. So yes, we're going to see higher dust production with more angular grains, younger grains, than with grains that have been transported already and that have a higher roundness. Which is part of the reason why we crush them exactly for the coral pink. Coral pink is very well rounded. It's been transported for a very long time. If we want to get an idea of how that particular mineralogy is affected or how that contributes to dust, we need to make them more angular.
How about dust production in basaltic material versus these quartz grains?
Yeah, and that's exactly why we're doing those comparisons. If I just did the well-rounded material versus the angular Pisgah Crater, then I don't get an idea of how rounding affects between the mineralogies.
Do you actually have Mars then, or are you just in like a close mimicry of how Mars then behaves?
Yeah, so are you talking about the environment or the sand itself?
The sand.
Yeah, the sand itself, so it's an established Mars analog. There's a database of Mars analog sands. So these sands are analogous to what we see on Earth. So their mineralogies match, on Mars, their mineralogies or compositions match what we see on Mars from the remote sensing data and from the data on the ground in the rovers.
Okay, we need to move on.
Yeah.
So, next up is Connor Early from Arizona State University.
Okay, I'm trying to go a little quick since we're a little over. But hi, I'm Connor Early. Thank you all for coming. I'm a senior in astrophysics at ASU. For the past 2 to 3 years, I've been working with faculty mentor Dr. Nathaniel Butler and graduate student Lee Bernard on this NASA Excite project, where we're doing the Sense for Exoplanetary Climate Infrared Telescope. We're trying to perform through innovative instrumentation and spectroscopic techniques. We're trying to look at some exoplanetary spectroscopy. There's a little overview. First, we'll go into the introduction, which will introduce the scientific question and how we're going to address it. And then we will feed into the science objectives of our mission and the background for phase resolved spectroscopy. And then we will go into the ASU's main contribution, which is a spectrograph, and our instrumentation techniques, and then current endeavors and some outlook and discussion. So first off, as of now, over 5,500 exoplanets have been discovered to date, but very few have been characterized. So we know almost nothing about their atmospheric composition, thermal structure, and planetary dynamics. Previous efforts to characterize these things have largely relied on space-based observatories like HST or Spitzer, but those have a lot of issues. They're super expensive, telescope time is very competitive. So we want to change that. We want to bring it, we want to make it more accessible. So we're building this telescope. It's called Excite. It is a long-distance ballooning platform. We're planning to fly in Antarctica in the next upcoming years. We're analyzing some close-in, tidally locked extrasolar giant planets. And then we're going to be the first ever dedicated observatory for phase resolved spectroscopy. As of recent, 2 attempts have failed using JWST time, so if ours does work out, we will be the first people ever to produce that kind of data.
Okay, so some science objectives. EXCITE is, the science objectives are super broad, but to just give a few, phase results spectroscopy will allow us to map the temperature distribution and atmospheric dynamics and chemical composition as a function of longitude. We are flying in the upper stratosphere, so we almost have 100% transmission in the near infrared from 1 to 4 microns. This will allow us to constrain the global energy budget of the hot Jupiters and look into the radiative and dynamical timescales of the planet's atmosphere. People have often speculated for a long time that brown dwarfs' atmospheres and EGP's atmospheres have very similar spectral classifications, but there's been very few engineering and science missions to search for evidence for that. So phase result spectroscopy can probe very high pressures and temperatures, so we will be able to look for similar M to L and L to T transitions. That's the loss of silicate clouds and the loss of titanium oxide absorption features in the spectrum. So phase resolve spectroscopy is pretty much exactly what it sounds like. We're observing the EGP for the full orbital period, and then we're analyzing the spectral features throughout the whole orbit, hence phase. We'll be able to gather data on the dayside emissions, which will give insight into the temperatures and thermal properties and atmospheric dynamics, as well as like emission spectra from the transit, which will give more insight into the chemical composition. So here's sort of what a simulated phase curve spectral retrieval looks like for WASP-18b. As you see, there's three graphs here, one for each phase, 0.02, 0.25, and 0.5. We can technically do this for any phase we want, and from here we can get a pressure versus temperature gradient at each phase as well. So this is our ASU's main contribution, is the spectrograph. It is a 2-channel spectrograph. It has dichroic. It reflects 1 to 2 microns and transmits 2 to 5 microns. It's a slit spectrograph, so the focus of the telescope is dropped onto this slit assembly here. It's reflected all the way through. We have a dispersing calcium fluoride prism, which does the heavy lifting. And Goddard Space Flight Center was kind enough to lend us an H1RG IR detector. So that's that thing right there. It is fairly low resolution, but we don't need super high resolutions. We just need super high sensitivity to view like phase curve offsets and amplitudes. But due to this detector, it's cool. It has to be cooled down to 62 degrees Kelvin. Okay. So towards the end of last year, we started to actually get parts and the optical mounts, and this was basically just to hone some alignment procedures. And then Goddard was like, oh yeah, you have like 2 weeks to get to here. So we like rushed, and then we tried to paint it ourselves. That failed. And then, so we sent it off to a local company in Tucson that's a professional at painting these high aerospace parts. So this is U306 paint. It's a high emissivity paint. We aligned this 45-degree OAP, which is the main driving factor of the alignment and all that good stuff. So this is where it's at currently. It's currently in the Dewar, which is a cryostat in Goddard. And our current endeavors are simulating the spectrograph using these 2 powered optics, which are 30-degree and 45-degree off-axis parabolic mirror and the 2 focal planes. So this aperture and this flat mirror. So this is the detector, this is the slit. So right now as it stands, we have engineering alignment at room temperature. We're trying to generate some non-invasive alignment procedures so we don't have to take it outside of the Dewar, and check for alignment as we cool down under cryogenic thermal loads. So some outlook. We did try and do an engineering flight in Fort Sumner last year towards the end. That didn't work out. Super warm El Nino. We had a super big Hadley cell that encroached really far up, which created super annoying crosswinds. But yeah, Antarctica and the Antarctic in the upcoming years. And if we do get data, we'll be the first to produce some phase resolve spectroscopic data. And then given all of that, once we gather the data, we're going to put it into 3D general circulation models, which give like a 3D model of what the planet is doing. So we'll be able to look at cloud formation and all that stuff. And if we see anything very interesting in the individual planets, we're going to use JWST to perform some more narrow band but high resolution spectroscopy. That's it.
Yes.
You mentioned like the different phases, and it seemed like there were two periods that
What's up? Here? Oh, this one. This one.
yeah, so those sort of like two periods that you're looking at.
Yeah, so the most useful data is right here and right here. So that's when we get the most, we're able to view the day side of the planet the most because it's tidally locked. So.
So what's like the time period between like one day going to like, all right, we can't add.
Oh, so we are collecting the entire time, but these are just our most useful points. So that depends on our parameter space and all the planets that we choose, and yeah, the orbits.
So what's the orbital period?
A couple of days, most likely. I think our flight is like 30-ish days in Antarctic, so we'll be able to observe like 5 or 6 planets at a time.
All right, we have time for one more.
Hey, what cooler are you using to cool down that thing? It's a 64 Kelvin. What is it?
It is. I'm not quite sure. That's a totally other university that's doing that. We're solely responsible for the spectrograph, but it is liquid nitrogen. It transitioned from, I think, solid nitrogen to liquid nitrogen or something like that. I'm kind of unfamiliar with that kind of realm.
All right, we need to go ahead and move on to the next. So next up, oh, go ahead.
Thank you.
Is Dora Elalawi.
Yes.
And she is from the University of Arizona.
And do you know if this is being recorded? Okay, hopefully. I think it's being recorded because I think I want it recorded. I've declared that. Okay, cool. All right, so hello everyone. My name is Dora Elalawi-Pinedo. I'm a sophomore at U of A, and my project was mapping enigmatic pits in the North Polar Layer deposits of Mars. I worked with Dr. Sarah Sutton. She's on the high-rise team at LPL, and this is my project. Cool. So there are these meter-scale pits, holes, that show up in the North Polar Layer deposits of Mars, and they're mysterious. We don't know how they formed and why they're there. So using high-res images from the high-resolution imaging science experiment aboard MRO, we can look at these images and find these pits and then map them out. So we map them using QGIS, and in order to do so, we can eventually find or try to understand the formation mechanisms and spatial distribution among the NPLD. And analyzing pits can hopefully reveal active surface processes in the NPLD and uncover Mars's climate history. Okay, cool. So hunting for pits. Pits are weird. They're meter-sized. 1.5 meters is about my height. That's their diameter. So they're a pretty big hole in the ground. We can't see in them. They're super dark. As much as we contrast an image, can't see any light within that image. And they usually appear within the walls of troughs. They're kind of exposed within these layers, and you can see that they just show up and they're there, and we don't know why. Sometimes you can see this like little crescent that's reflected around the edge of a pit, and it could be a frost residual or something else, something we're looking further into. And like I was saying, they're 1.5 meters in diameter. We have found some that are a little bit bigger than that. And we use high-res images to find them, and then QGIS, a geographic information system, to map them. So here's some example of pits. On the top in the green, you see that these are some circular holes in the ground. That frost residual right here on the side, that could be a frost residual, but that's a crescent that we're using as a characteristic to help find them. The red is not pits. These could be shadows caused by small rocks or boulders. Just things that don't clearly necessarily define or align with our pit identification criteria. And then the blue is possible pits. These are just something that we're looking into, but we can't really define them with our definition. So here is our current map. So the base map, the gray all around, is from MOLA data, and on top, all the rectangles are high-res image footprints. So we've divided this map into 30-degree longitude bins. The green means that pits were found in those images. Red means pits were not found. Blue means that there was possible pits in there, but something we're looking into. Then purple means bin 2, which means that these are images taken by HiRISE that are not at the highest resolution, so we mainly look at bin 1 images for now and prioritize them. The orange are pit locations, and we'll get a further close-up look of that. The stars indicate NRC pits, which means pits that are on this uppermost layer of the NPLD, so they could have different formation mechanisms, but we'll go into that a little bit further. And then the white means pits that have not been, images that have not been viewed yet, and something that we can look into. So here's a close-up. You can see that there are pits here, and then we'll get a better image in a moment, but these are troughs, and these pits are showing up on these walls of troughs. So here are pits. These are not to scale, but they're very, very small dots on here, and that's where they've been showing up, some interesting things. And we'll get to some results. Here they are, 2,025 pits found. So there's a lot of these weird holes that are just showing up, and we're not understanding why. So out of the 422 images that I was able to view, I saw pits within 75 of them, and I focused mainly on those trough areas. So then I found some new pits in the north residual cap, which is that uppermost layer of the NPLD, and they're possibly along a fault line, but something we're looking into. Like I was saying, pits are mainly along troughs, the walls of troughs, and they're not found in the basal unit, which is the bottommost layer of the NPLD. It's usually low albedo, so light isn't reflected as well from that bottom layer. So these are the pits that I had found. They show up in this linear pattern, kind of indicating that they could be fault related. And then here are two locations that were previously known that were pits showing up on that uppermost layer as well. These could have different formation mechanisms. So in meters, we noticed that our pits kind of showed up in this negative 3,500 range, which could indicate something. This is something we're trying to do further analysis on. Additionally, slope was interesting as well. So our pits have been showing up on very moderate, like gradual slopes. Could mean something that maybe they're on the equator-facing slopes, which are usually a lot more module and gradual compared to the pole-facing slopes. So, like I was saying, this is some pretty novel research, and all this data is going to help provide information into understanding how they formed. So, like I was saying, these pits could be on equator-facing slopes or pole-facing slopes. We want to find out more specific measurements of pits and see their exact diameters. We also want to see if pits could be found in specific layers. Maybe they're occurring along certain layers in the NPLD. We want to compare the trough pits to those NRC pits, see if they have different formation mechanisms, see if these pits are actively forming today, and that would require a time analysis, looking at images over multiple Mars years. And can trends and aspect point to wind, isolation, and erosion formation processes? Something we're looking into. I want to acknowledge Sarah Sutton. That's Sarah Sutton. She's a great, great, great mentor. Yes, thank you, Sarah. The HiRISE team, great group of folks, LPL, University of Arizona, and NASA Space Program. And thank you.
Hi, Mark. I was wondering, how do you guys know that these are native relief, and also is there any seasonality associated with these?
Ooh, interesting. Yeah, so seasonal is something we were looking into. So sometimes the pits show up when they're in a frost-covered zone, or sometimes they're not. So it could be seasonal related, but that would require more of a time analysis, looking over different Mars years and seasons. But yeah, there's so much analysis to be done, but they're very interesting. Yeah.
Is there a reason that you opted for QGIS over another GIS software package like ArcGIS Pro or ArcMap?
No specific reason, and maybe I just like the name better. I don't know, but yeah, QGIS was our main use.
Other questions?
No. Yeah, and so we're planning on hopefully doing a digital elevation model and see if that can help us understand how deep they are. But as of right now, we cannot, even with the high-rise images, understand because light isn't being. Yeah. Something we're looking into. I'm not really sure how deep they could be right now, but who knows? Maybe.
So, I got a question. Maybe I think you said this. So
Yes.
what is the substrate material? What is the material in this one?
So the NPLD is layers of dust and water ice, and their composition is very interesting. Like it's just layers of just all this sedimentary, and then you have ice that could be depositing or sublimating. So it's just this really interesting mixture. So yeah, that's where they're showing up in those specific type of layers.
Other questions?
What's the rectangle, what's the coverage area?
Yeah, so like a high-rise image footprint, those are about 5 kilometers across, which is about 3 miles. So 422 images that I saw, and then that's a good amount of area I looked at in the NPLD. So.
What, I know you don't know a lot about kids, but do they differ all from like if we get singles here, do they behave the same?
Yeah, we are like looking into different things that could be similar to them, and they could be caused by like wind. There's strong winds over there, and maybe they're just opening these holes. It could be something where maybe like ice is melting in. It could be anything or a sinkhole, something. Those fault-related ones, maybe they're going in because they're cracking because of the fault. So it's interesting, but yeah, it's something to look into.
Okay, let's thank our Next up, we have the Ascend team from Carlson Union High School. So, come on up, Oscar Ryan. All right, so you're going to use, I'd like to use the microphone, so don't have to be hard. And what you're going to have to do too is you're going to have to keep walk up to the microphone. So be ready. And then this is the pointer. So the green line is the laser. And the arrows are forward and back.
Hello, we are the Cascaran Union High School Ascend team, and our project is exploring the Martian agriculture frontier, assessing tomato adaptability through high altitude experimentation. My name is Landry Howard. I'm the team lead as well as the science PI, and these are the rest of our members who will be introducing themselves throughout the presentation. Our mission statement is that we will design, construct, test, and fly a high-altitude balloon payload to gather atmospheric data and 4K video during this flight. Our bioscience experiment is tomato seeds. The tomato seed experiment is for us to study whether or not plant life will be able to be grown on Mars. The goal with this experiment is to study whether there are any mutations in the DNA of the tomatoes after being exposed to direct UV radiation, lack of oxygen, and extreme temperatures. We will be planting, harvesting, and flying seeds from the tomatoes that were sent up previously, continuing this for 5 generations, keeping control groups of seeds for each generation and DNA testing each batch to find differences and/or patterns in the DNA.
So this is under the Ascend project. Now, what is Ascend? Ascend is a project where we create a payload where you put sensors in it and you use it to solve whatever question you want that relates to the atmosphere. You send it about 90,000 feet up before the balloon bursts, and it goes plummeting back down to Earth. Specifically, my name is Elijah Ramirez. I am the mentor for the fabrication team. I have done this project 5 times, so I wanted to step away from the more hands-on approach of myself and hand it off to our interns. This is one of them now.
Alright, my name is Zechariah Buchanan, and I was the intern who was tasked with making the CAD models for the payload. So if you can look on the screen, you can see that the CAD model is obviously a hexagon. We decided to go with a hexagon due to the issues with last time. Our payload was too small, and we had issues with just like the wires were either getting broken or they would just stop working because they were in too tight of a space. Also, having such open having such an open space, it allows for heat dissipation a lot better. It allows for not everything to overheat so quickly in a small confined space. Everything overheats a lot quicker. I'd like to pass it off to our other senior.
Hello, I am Melody. I am a senior on the fabrication team. You may be wondering some more specifications about the size of the box itself. The box itself is 7 inches tall. Each outside panel is 6 inches across, and from flat side to flat side, it is 12 inches all the way across. The foam itself is 1 inch thick. For specifications about the materials we used, the main base of the payload is made out of Armax foam, which is held together with wood glue and a layer of duct tape. And then we also have a Lexan panel covering the camera. That way we can still see out with the camera, but it's more protected when it comes plummeting back to the ground. Over the tomato seeds, we have a quartz plate because quartz allows UV radiation to pass through. So that way we'll be able to tell how that affects the tomato seeds. I will now be passing this on to Aliciana, our design fabrication intern.
Hi, I'm Aliciana, and I'm also on the fabrication team, and I designed the top lid of the payload. We choose the base on Pokemon named Lunala, and the process, it was fun, like sketching and painting it, and it's overall a really good experience.
All right, I'm Ethan. I'm the lead programmer for our team. So we have to actually get data somehow to do any research. We're not going to know mutations in the tomato seeds if we don't know the temperature or the altitude. So the way we did that is code. We have an Arduino. I use the Arduino IDE and C# to code something like this flowchart. So we have our BMP390, which does temperature, altitude, and pressure. And then we have our analog read UV sensor. And then we have our SD card reader, which likes to give me problems. So this is kind of how the code works. It goes through the SD installation, and then the SD card will create the file that the data is actually going to go on. And then from there, it checks that the BMP is on, makes sure it's not off, checks that the UV is going, and then it starts reading data in a loop every about 5 seconds or so. And then it will write that data to the SD file, and then we'll have our awesome data. This is how we actually did that electrically.
Hello, I'm Emily. I'm a junior, and this is my first year doing Ascend. So for our power circuit, we had what is this? 2 9-volt lithium batteries that we wired in parallel, which connected to our switch and our voltmeter, which allows us to control the power from outside and see it's on and off. And then we connect that to our Arduino Uno, which has our BMP390, which is wired in I2C, and our UV sensor, which is in the analog read. And that outputs onto our SD card reader wired in SPI. Hopefully that actually works this time. And we, separate, we have a 4K video camera, and we were going to have a Geiger counter, but we had to remove it due to the space limit, or not space limit, I'm sorry, weight limit. And then here's just pictures of the circuit outside of the payload, sorry. And yeah.
We would like to say thank you to Michelle Coe, Clayton Jacobs, Stephen Thomas, Shirley Campbell, and our advisor, John Morris. Our poster was number 6, so hopefully you had a chance to check that out. Thank you.
Do we have any questions?
How does sending the tomatoes into a high altitude environment relate to a Mars environment?
I'm sorry, what was your question? I didn't hear the last part.
Sorry, how does sending tomato seeds into a high altitude environment relate to a Martian environment?
This is the closest we can currently get to testing how the tomato seeds will react to being in that environment. So that's how we're testing it.
How do you guys plan on testing the tomato seeds' DNA to see what's changed?
Once the tomato seeds have fully grown, we will be handing them off to the biotech students at our school, and they will be testing that.
Great talk, guys. Is there any reason that you would, besides just that Ascend is a ballooning project, is there any reason that you would choose to do this work, maybe financial, using a balloon instead of in a laboratory?
How so?
Just like what are the advantages of using balloons instead of, I don't know, like a Martian simulation chamber?
Well, the thing is, with balloons, the difference between a Martian simulation chamber and balloons is with a balloon, we can go to space, I would say, both a lot cheaper than simulating, building a room, clean room, than simulating the Martian experience. With a balloon, we can send it up to space, and if there is a certain atmospheric pressure or difference where we want to, like, if the atmospheric pressure at 100,000 feet, 75,000 feet up was similar to another planet, we could then send the balloon up, have it build the balloon to top at that level, and we will get data at a similar level without having to build the entirety of an enclosure just to simulate one test.
Yeah. And also so that we can, up there, if we actually just send it up, we just get the UV directly from like what it would be like up there. So it's more of like actual real life, what it would be.
It's very similar conditions.
You got a question over here? Go for it.
I just have a quick question regarding the radiation shielding. Do you guys use it radiation shielding because for like the microcontrollers and electronic hardware, or is it even considered at that altitude?
No, we do not use any of that.
It would kind of just go through anyways, but for a lot of what we use, that could use.
So quick, yeah. So you said you were recording 4K video. If that's going to be the whole way up, how big is your SD card? How are you going to store all that?
I believe the SD card is 60 gigabytes.
It works. Eddie?
The same. I think you guys are sending out the tomato seeds up there, right? The thing is that perhaps what happened is that maybe pre-lunch and after lunch, if you guys want access to the scanning electron microscope at your couch, we'll need to give you access.
Okay, thank you.
Thank you.
Yeah.
Well, I'm wondering, what's just the way that just the enclosure, sans the payload and all the other stuff inside, the phone. How much did it weigh?
Just the enclosure, if I'm correct, if I'm remembering something well, the enclosure weight was, wasn't it near a pound? 2 pounds? Yeah, it was near about 2 pounds, I think. Maybe a little less. Maybe. Yeah, without the electrical, it's near 2 pounds.
One more. Tim.
No. Our SD card fried, and so we didn't, and so all we got was the video. We didn't get any other data.
Things were too close together, sides would get heated up.
That's why we decided to use the hexagon. We used the cube last semester, and it got very hot, and we learned when we opened it that the SD card reader had pretty much fried, so we had pretty much no data.
One of the issues.
Yeah, we had multiple faulty readers.
Yeah, also,
I don't like
the USBs, they are controls, and the ones we send up both die.
Yeah.
So, like the seeds were both just dead.
Yeah.
All right, so I want to add one more bit of information. We weren't able to launch this spring because the jet stream was not very cooperative, and we did not have good conditions for launch, but we're hoping to launch yet this spring. So stay tuned. We will get that payload in the air, and you can get some data. Now it's time for our break. So we have a break until 10 after the hour. So be back here at 11:10 if you want to be in this session. But let's give the consequence music. And all our speakers. So we had great talks today. So thank you, everyone. Being so well